Here is an explanation for the answer to final exam question number 33, found on page 240 of Everyday Math Demystified, 2nd edition. This question will bring back memories of 5 questions ago. That is question 28, which we were concerned about the mass of a rock and what would happen to that mass if we moved that rock to a planet where the gravitational pull was only half as powerful as it is here on Earth. Well, let's say that we've got this rock now again, and it so happens in this scenario on Earth that W, the weight of the rock, is 10 pounds. If we take this rock to a planet where the gravitation is only half as strong as it is on Earth, what's going to happen to that weight? Well, the answer to this particular question is D. The weight of this rock is going to go down to half of what it was, or only 5 pounds. The mass of the rock will remain the same, but the weight will go down to half because the gravitational acceleration or gravitational pull will be half as great, so it'll only exert half as much force on the same mass. And weight is in fact an expression of force. When we talk about pounds, we're not talking about mass per se, we're talking about the force on a mass. That's why if you ever watch the videos of the astronauts on the moon, you may have noticed that when they jumped up and down, they seem to be moving unnaturally slow, and they seem to go unnaturally high because, in fact, they weighed a lot less on the moon than they did on the Earth. Their mass is still the same, but their weight was less. So if you take something, no matter what its mass is, and put it out into intergalactic space, where there's no gravitational pull at all, it will be weightless. It won't weigh anything, but it'll still have inertia. That rock will still have inertia. If you take a boulder, say it weighs a ton on Earth, or 1,000 kilograms, say, of mass, and you take that out into space where there's no gravitation, you're still going to find that it has a tendency to stay where it is or to move in whatever path it's moving. And if you push on it, you're going to have to push pretty hard to make a difference. So the mass stays the same, but the weight depends on the intensity of the gravitational pull. Again, D is right.